Hello and welcome to the webinar. My name is Josh McDaniel and I work with the Wildland Fire Lessons Learned Center. In just a few moments we'll start the webinar. First I want to make a few quick notes and announcements. First I'd like to point out that the webinar is a part of a webinar series, and the webinar series is sponsored by the Joint Fire Science Program, the International Association of Wildland Fire, and the Wildland Fire Lessons Learned Center. And so we've been doing this for a couple of years now, and we usually have 1 or 2 webinars per month, usually a little less during fire season, a little more during the winter. But keep checking back with us to see upcoming webinars. The next one in the series is listed here, and that's the Bob Keene is going to be presenting on fire management fuels and climate change tipping points. So we've got a sort of a climate change theme going in that last month or so. You can register for that webinar at, I put a link up there. I put a bit.ly address to make it a little easier to find. But the page is Advances in Fire Practice. You can also get to it by just Googling Advances in Fire Practice. And right at the top there is where the listing of all the upcoming webinars, and you can click on the links and register. Okay, so I'll introduce the speaker for today in just a second. But first I want to point out how questions work. We encourage you to get your questions in early. The quicker you get your questions in, the farther up the queue they are, and the better chance we have of getting to them. And you can just type that right into your question or your chat box down at the bottom of the little control panel over to the right, and we'll have a Q&A session at the end of the presentation. Okay, also want to let you know that the webinar is being recorded, and the recording usually doesn't take too long these days, about 20-30 minutes after the webinar. We have that uploaded on the Advances in Fire Practice YouTube channel, the Wildland Fire Lessons Learned Center YouTube channel, and you can go to Advances in Fire Practice and it'll take you right to that. Or you can email me, and I'll put my email up here in a second if you would like to get a hold of that link and pass it on to someone who might be interested. So I'll go ahead and present the speaker, introduce the speaker. Phil Van Mantgem is the presenter today, and Phil is a research ecologist with the U.S. Geological Survey, and he's stationed in Arcata, California. And Dr. Van Mantgem's research interests include forest dynamics with an emphasis on climate change impacts, fire ecology, and the management of forested ecosystems. He received his doctorate in ecology from the University of California, Davis, and has been studying and enjoying forests since 1995. And with that, I will hand it over to Phil.
All right, well, thank you, Josh. I appreciate the intro, and I thank everybody out there listening in for taking time out. This is a busy time of year, and I appreciate you tuning in and listening to what I have to say here. So our topic today is, can our forests take the heat? Fire and climate change and tree mortality in the western U.S. And just to launch into this, we all know that there's a physical context to fire. So this is our classic fire triangle with topography, weather, and fuels. And if we understand topography, weather, and fuels, we have a good idea of what fire is going to do. In fact, it's been incorporated into a lot of the tools that managers use to try to understand what fire is going to do on a landscape, what the effects are going to be. And essentially, again, what we need is this information on the physical context of fires. So again, fuels, weather, and wind data. And sometimes they've been incorporated into spatial information for things like FarSight. And there's a series of very elegant sort of models, physical models of how fire is going to respond to that physical context. And once you understand that, we can start going on to fire effects, so things like fire behavior, fuels, air quality, and so on, effects on vegetation. What I'd like to talk about is one aspect of fire effects, and that's tree mortality. And for tree mortality, essentially the take-home message that I'd like to communicate to you all is that there's also a physical and a biological context to a fire event if you're trying to understand fire severity in terms of tree mortality. And for a little outline, so this is where I'm going to be going for the rest of the talk. So just as background, this is probably familiar to a lot of you, is predicting post-fire tree mortality. How do we understand, or how do we sort of quantify what affects a tree in terms of getting burned, and what's its likelihood of survival? Next, I'd like to move on to improving these predictions and really sort of bring home the idea that pre-fire conditions can also affect post-fire tree mortality. And then finally, I'd like to talk about what does this mean, especially for people that are in a management position. What can we do about these impending changes that we're that we're likely to see going forward. So first of all, why tree mortality? Well, forests or trees can do one of three things. So they can grow, they can reproduce, and they can die. And this is a very cheesy schematic, but really if you understand how fast these things are occurring, you know a lot about a forest system. So you understand their population dynamics. And one of the things that we've been finding over the years is that tree mortality is not only hard to measure and hard to quantify, but it also determines the population trajectory of a forest stand. And so if you make small changes to a tree mortality patterns, you can have big changes in the forest. And that sort of speaks to a very intuitive concept that you can kill a tree a lot faster than you can grow a new one. And you can quantify that and you can put it into fancy forest simulation models, but it basically comes down to that idea that tree death can happen rapidly, tree growth and reproductions happens relatively slowly. So tree mortality, it's important. And how do we predict post-fire tree mortality? Typically what people do is looking at individual trees, they look at defense and damage parameters. So by defense, things like crown height, the thickness of the bark, sort of the layer of insulation that it gets from being burned, and then also the damage. How much heat is it exposed to? How much crown scorch does it experience? What's the length or height of the bole char? And sometimes people have tried to quantify root damage. And to begin with, let's just take a look at crown scorch. So crown scorch is probably the single best predictor of post-fire tree mortality. And in this graphic on to the left of the screen, you can see a scorched tree, and you can see that this fire, the heat plume didn't scorch the entire tree. There's still some live crown left. And you can fit that into a mathematical relationship. Here it looks like crown length killed, and it's non-linearly related to the probability of tree mortality. So as you get up to 100% of the crown scorched, you're having almost 100% chance of the tree dying as a response to fire. Another way we can look at this is also either the bark thickness or the bole char. How much is that bole experience? How much fire is that bole experiencing? And we can relate that not only to the thickness of the bark, but also sort of the length of time that it's been exposed to it, to heating. And so if you look at things like the amount of bole char on there, you can look at unburned to deeply charred stems, and they have a higher probability of mortality as a result. So it's those things in combination. And that's captured in a lot of predictive models that are used to try to understand fire effects. And so they'll combine things like bark thickness and crown scorch volume. Those are on the horizontal axis. On the vertical axis, we have proportion of tree mortality. And you can fit that into a simple linear model where you just combine those two effects, and you have a probability of mortality for an individual tree. And this is sort of the working mechanisms behind things like the FBS fire simulation module. So that's sort of where we're starting at. And can we improve those predictions? What else could we put in there that might improve our ability to understand what's going on? As some background, there's some pre-fire conditions that are changing that we're observing right now. So this is just a little walkthrough on what's going on, and I probably don't have to tell many people on this conference that things are getting warmer, they're getting drier, and right now we're experiencing drought, a long-term drought in the western states. As a result, partially, of those trends, we're seeing an increase in area burned. And here's a graph of the area burned across the western U.S. And you can see that we had a large area burned sort of back in the 1920s and 30s. Throughout the 50s, in those decades, there is a decrease, and that's probably a lot due to fire suppression and our sort of successful tactics with that. But then it starts creeping up again towards the end of the 70s. And that could be for a number of different causes. Some of it is fuels buildup, but some of that increase in area burned is likely due to climate. And here, I thought this is an interesting trend here. This is, again, the area burned sort of on the left-hand vertical axis, but also the dollars spent on suppression. And so we can see that we're still seeing, in recent decades, an increase in area burned despite more and more resources going towards suppressing fires. And here's sort of a fundamental research result showing an impact of climate on western fires. So this is mostly coniferous forests in the western United States. And what they're finding in this upper graph is that temperature, sure enough, was increasing, and that was correlated to wildfire activity. The middle graph shows the timing of spring snowmelt, which gives you an idea of how dry those areas are going to be. And the anomaly is showing sort of an increase in the early season. So that line in the middle is trending towards that pink area. And then finally, if you look at fire season length, it's sort of the width of that, the red and the black line together. And that's showing that fire season length, as a result, is increasing. So they're able to tie some of this increased fire activity into what's going on with the climate. More recently, a concern has been the increase in high severity fire. And if we look at this graph, this came from a recent paper, again, mostly in the Southwest, but they're looking at wildfire area burned, and that was for moderate and high severity fire. And they were able to find a very tight correlation with what they call the Forest Drought Stress Index, which is trying to combine the idea of cold season precipitation, so winter rains, snow, that sort of thing, subtracted by the warm season vapor pressure deficit. How dry is the system? And so as things essentially warm up and dry out, we're seeing an increase in fire severity across a large area of the United States. And getting back to forest mortality. So here we have our graph again, and if things are drying out, not only is fire changing, but the background forest dynamics are also likely changing. And this is some work I was involved in looking at old growth stands across the western U.S. There's not very many of them that had adequate sort of sampling going on there, but where we could find them, so we had 76 sites across the western U.S. Where we had good demographic information on what the forest populations were doing. And in the graph, the red areas are increasing in mortality, and the size of those symbols corresponds to the magnitude of change. And there's some areas that were also decreasing in mortality, but very few of them, to the point where 87% of the plots were increasing in mortality. And these are old growth stands. We wouldn't expect any sort of directional change here. We'd expect there to be a balance between increasing and decreasing mortality, or essentially just no trend. But that's not what we found. Things are warming up and drying out, and likely trees are dying. This has actually been more or less replicated in a way in Canadian boreal forests, where they found records of, again, old growth stands, or old forests anyway, and finding increasing mortality rates where they had records. And interestingly, just this year came out a study on boreal forests, but sort of young versus old forests, where they're finding similar sorts of trends here. And this is not the greatest graphic to show this, but in the upper panel there, they have the year effect on the parameter of mortality, and it's positive, so it's increasing for the important species up there and across time. And what could be driving that trend? What we were looking at least in this year, where we had some fairly good information on trees that died standing, it looked like it was related to what we call climatic water deficit. And climatic water deficit is just a way to incorporate precipitation and temperature at the same time and try to get a sense of what the soil moisture is doing as well. So it allows us to, it gives us a nice biologically meaningful index of drought. And here we're seeing in this graph for standing dead trees in the Sierra Nevada, what we're seeing is an increasing mortality rate, and that's paralleled by this increasing water deficit. So it's correlative, but it's a very suggestive correlation. And another observation that's been going on is that dieback events in western forests appear to be becoming more common. So here's a graph, or here's some pictures taken by colleague Craig Allen in the Four Corners region during a pinyon pine die-off event at beginning of the last decade. And this is just sort of showing the landscape level, sort of what it looks like when you have a big die-off event. It's not very pretty. And he took together sort of observations from across the globe, and he's finding that there was an increase in dieback events, or at least the reporting of dieback events. And those reports seem to be concentrated in areas that were sort of arid to begin with. So these dieback events might be becoming more common. Now, what might this have to do with fire? So we took the idea that these stands might be more stressed out to begin with because of drought or increasing temperatures. And then if you apply fire to it, those stressors might interact with each other. And there's a number of different examples that you could use from your own life for how stressors might interact. But this might be one of them. And to take a little sidebar, this is how we conceptualize tree mortality, how these interacting stressors might affect tree mortality. And we have this nice conceptual model called the decline spiral model of tree death, where you start out with a healthy tree. It gets affected by some stressors, say competition. It gets suppressed. It might be more affected by drought, and so on, as it sort of suffers the slings and arrows of things that could take advantage of a weakened tree, and eventually it dies. Another way to draw that same concept, the decline spiral model concept, is this way. It's more sort of a Cartesian format, where if you had a high vigor tree here, so high on that vigor axis, and it's impacted by drought, it might be able to recover and keep chugging along. If you have a low vigor tree, say from something like acid rain, it might not be able to recover as well. So things like gypsy moth, root rot might come in, and eventually the tree dies. And our thought was, well, you could take the same concept and apply it to fire. So instead of drought as your stressor, how about looking at fire as a stressor? And this is what we did for, again, we put together a simple logistic linear model here. So we have crown scorch, just like what we saw for earlier, but then we also applied radial growth. And radial growth is our index of vigor, how healthy a tree was. So we had 5 years growth, we looked at the fire damage and its probability of mortality after getting burned. And lo and behold, this is what we found. So this came from a single fire at Sequoia National Park. This is strictly for white fir, where we had enough information. And if you look on the bottom axis here, we have percent crown volume scorched. And sure enough, the more you scorch your tree, the higher the mortality probability is. But then if you also look at the other axis at the bottom, we have pre-fire radial growth rate. And as a tree was growing slower, that is, it looked like it was less vigorous, it had a higher probability of mortality. And that was sort of influencing the shape of that relationship between crown volume scorched and probability of mortality. And so now we're interested, if that was occurring for white fir in one stand, we're interested, is this occurring at a larger scale? Is this a general sort of relationship? Another thing that we're looking at was sugar pine, so in the same area in Sequoia National Park. And it was a species of concern because it tended to die off in a lot of the prescribed fires. And that's not what we wanted. We wanted to conserve those trees as best we could. And this is some work done by Johnny Nesmith, who's now working for the Park Service. And what he was finding that an index of crown health seemed to predict post-fire mortality. So as trees were healthier, they were more likely to survive being burned. And this is for sugar pine. And again, we could put it in terms of probability of survival. And I think this is kind of an interesting result where the immediate post-fire relationship, if you look at the dashed line here, it was all about just the crown scorch and bole char, sort of what we're already capturing in our typical models. But then if you look 5 years out, the delayed mortality, what became important was those sort of injury parameters, but also the 30-year growth trend of a tree and the 30-year count of sharp growth declines, sort of index of vigor that we found to be predictive of mortality in unburned stands. So there seems to be some relationship between the pre-fire health of a tree and its probability of mortality if you account for all the other injuries that it occurs. And then what we really wanted to know was, is this relationship widespread? So we just had 2 species in Sequoia National Park, and does this apply to the wider spectrum of forest types that we have in the western forest? And to get at that, we accumulated data from the National Park Service and the U.S. Forest Service. So we had 18 sites, a whole bunch of plots, 7,000 trees, mostly in areas where they're doing prescribed burn, because there we could get information on what the pre-fire status of the tree was, and then also some nice measurements post-fire. So the amount of injury that it sustained and its mortality 5 years out after a fire. And this is what we found. So we started out with a base model where we're considering bark thickness, crown scorch, and bulb char. To that, we added what we termed relative deficit. So again, this climatic water deficit, and what we're interested in, because we're comparing a bunch of different sites, what the long-term, what the pre-fire climatic water deficit looked like relative to the longer-term average. So relative to the long-term average, was it dry or was it not? And what we found is that that relative deficit was predictive of mortality, and it was interacting with the crown scorch and the amount of bulb char that it got. So it's not independent. They seem to be working together. And this has some nice parallels with some recent findings in tree physiology. First of all, if you look at just drought mortality, Bill Anderegg just this year came out with some stuff showing that there might be evidence for what he called cavitation fatigue. That is, trees that experienced drought in the past were more sensitive to drought in the future. So if you look at this little graph, the black line and the black triangles were trees that were exposed to drought before another big drought event, and then they had a higher probability of crown mortality, and the xylem or the conductive elements weren't working as well. So long-term drought seems to be a factor. And then some other interesting recent results were also showing that heating from fires, besides the injuries that they cause directly just from tissue necrosis, it also causes cavitation of the xylem system, so that column of water that's being pulled from the roots to the crown of the tree. If you get a water bubble in it, it doesn't work so well anymore. And what they're showing is that just sap heating and a higher vapor pressure deficit from the heat plume of a fire was actually causing cavitation. And there's also xylem element deformation. So xylem, again, is just these, essentially these little empty straws that are going up and down the tree and pulling water up that from the roots to the crown. And if you heat them, the polymers of the cell walls actually start degrading. So, and this is what this graphic is showing. As you warm them up, they get more and more degraded. So that there's, what we're finding in terms of drought and fire stress, it makes sense in terms of these physiological findings. And just as a final note here on this study, the sort of the severity of drought seemed to be increasing over time. So if we looked at the year of ignition, and each one of these dots represents a plot on the landscape when it was burned, we seem to have more trees that were or more stands that were getting burned when that relative deficit was rather strong. Okay, so what does all this mean? Why should you care? First of all, it's a kind of interesting result in that we can have higher fire severity without necessarily changing the fire intensity. So the fire intensity is the amount of heat released by a fire, and fire severity is measured by things like, say, tree mortality or depth of burn or something like that. And so what we're saying is that if you have a drought stress system, even if you have a rather benign fire, you can still get a higher fire severity than you might expect just because of that drought stress. So those stressors are working together. Again, this is the sort of biological context of the fire event. And we don't really understand this relationship, I don't think, all that well. So if we put it into our Rumsfeldian hierarchy of uncertainty, I'd say it would come out as one of our known unknowns. So there are known knowns, known unknowns, and unknown unknowns. So we know this is going on, but we don't really have a good fix on how it's operating or a lot of the driving factors behind it. And if we go back to our decline spiral of tree death, how might we incorporate this information into something that we can start working with? And we might need to start looking at it more of a systems perspective rather than a simple linear model. It's probably a much more sort of complex web of interactions. And that's some work that we're interested in doing going forward. Also, another thing that this might speak to is trying to understand or quantify fire severity. So typically that's done with remotely sensed images, and it's done looking at pre-fire versus post-fire imagery. And the post-fire is done typically right after a burn, within a year. And what we've been finding is that if you're interested in tree mortality, it doesn't all of it occur immediately post-fire. There's a lot of of mortality that occurs 5 or 6 years out even. And especially if you look at larger trees, they seem to have an elevated mortality rate for a good 5 years. So what this is showing is a burn mortality rate. This is sort of the dot and the lines. And this gray area is the background mortality rate for unburned stands. And it takes a while for it to return back to a background level of mortality after a fire. Another thing that we might be interested in is trying to do some carbon accounting from all this. So if we have increased tree mortality as a result, or if we're not accounting for all the tree mortality, that's going to affect or not help us with trying to understand the amount of carbon that's released. And this is some interesting work that was done, I think, on the biscuit fire. I could have that wrong. But they looked at the amount of carbon that's released as dead trees die and fall over and degrade, and they found it was higher than from direct combustion. So all the stuff that's coming up in smoke, that's part of the carbon emissions, but not all of it. And then finally, on management, we want to be part of the solution, not part of the problem. And at least for the agency that I do a lot of work with, the National Park Service, their natural resources policy says, when possible, try to restore and maintain naturally functioning ecosystems. And when this isn't possible, maintain the closest approximation of natural conditions. And our target has always been pre-industrial civilization on these areas, so 1850 or so on a lot of sites. And if that's our target, that might be a hard target to reach for these days, because the climate that underpinned that 1850 condition really isn't there anymore, and it's probably not coming back anytime soon. And this is particularly difficult with fire. We have long-term records going back that are very precise, and they give us a very good idea of what the fire regime was like prior to the era of fire suppression. But if we have changes in our temperature and our precipitation, and we don't really understand where those are all going, the past doesn't automatically provide us with targets anymore. It still might be the best thing, but we don't know that for sure. And here's a graph of what's predicted for California. And so we can see increasing annual temperatures over on the left, and precipitation is a little bit all over the map. So we don't really know if it's getting more or less, and the timing of it is going to change. And so there's a lot of uncertainty that we don't really understand here. And what does that mean for our forest? You know, if we have a warmer, drier environment or a warmer, wetter environment, that's going to mean really different things. So it's just hard to know what's going on in the future here. And so what can we do? So there's some ideas out there for adapting to climate change. This is one I like that was put out by the Forest Service a couple of years ago. And they go through some ideas of what can you do given all this uncertainty and all the changes and the sort of fast changes that we're expecting. So some of their ideas is using adaptive management, reduce the present threats as much as you can, things like invasive species. Monitor is a big one, and this is something that I keep running into as well, is that people want to see the results of monitoring, but nobody really wants to pay for it. And I think we need to figure out a better way of doing monitoring. And then we also need to start thinking about incorporating climatic change into management planning. And this is tougher because it takes us into some areas that we're probably not all comfortable with. So do we want to start thinking about things like assisted species migration, which I think generally is a bad idea, but we should throw it out there. Do we want to start introducing non-native genotypes? Do we want to start doing more intense thinning if we're expecting a warmer, drier climate? And these are tough things to start playing with because we don't really know what to expect in the future. And so if behind door number 2 is a huge catastrophic fire, how do we respond to things like that? At least within the Park Service, they're going down the road of scenario planning. And what this means is if you've got a highly uncertain future conditions and they're highly uncontrollable, things like climate change, things like adaptive management and probably won't work as well. But scenario planning is just the idea is that you try to play out what you think are reasonable possible futures and try to come up with reasonable management solutions to that, or at least responses that you could put into place. And the idea is that if you have a plan already and something like this does come to pass, at least you won't be caught off guard. So you'll have a way of responding quickly. And with that, I'd like to sort of tie it up here. So just looking in the future, we're really not sure what's going on, but we're going to keep plugging away. And so I'd like to say thanks to all the field crews and the managers and people like that helped me out with this. And if you're interested in seeing some of the primary research, if you want to read, we have some briefs of this stuff, and also the actual journal publications themselves. You can go to that website and look for fire ecology on that website, and that should take you to some of these things. So with that, I'd like to say thanks, and maybe I can go back to this and look for questions if there are any.
All right, Phil. Thanks. This is Josh coming back in. Yeah. So one of the when I read through the paper, one of the things that jumped out to me was when you talked about the management applications at the end, and you said this is something that managers have to be aware that there could be more mortality whenever they're not wanting more mortality, but there also could be scenarios where you might get more mortality and you're looking for more mortality. So I think I'll throw this out to the audience a little bit and see if maybe some of the land managers out there can sort of relate some of their experiences where they're seeing this, where they expected one result and saw another, or vice versa. They were expecting more mortality and they didn't get it, and that sort of thing. But so we'll see if some of those questions come in. Go ahead, sorry.
And I'd like to emphasize, too, what we're seeing was a fairly subtle effect. So, you're still capturing most of the variation with the models that are typically built into a lot of these planning tools. It's just that what we are picking up a signal from the antecedent climate, and I guess maybe the troubling or the thing to keep in mind is that we're expecting big changes in the climate coming up, and we've seen some already. Okay.
So there's some questions starting to roll in now, and there's two that are sort of related here, and maybe I'll combine them a bit, or see if I can. The first is from Carrie Metlin, and he asks, I'm not sure. You show strong trends with climate, but there is a parallel with increasing tree density with fire exclusion. How do you control for this? Maybe just answer that first.
Yeah. Okay. Certainly. Well, there's a couple different ways you can look at it. When we're looking at, say, this old growth trend in increasing mortality rates, you can build in things like basal area right into the model. And what we're finding is that basal area in a lot of these stands is actually decreasing over time. And so we can't really use that as increasing density in these stands as evidence of what might be driving things. You can also look at areas that have essentially not really experienced fire exclusion, so some of the higher elevation forests really have not had a big disruption in their fire regime, and yet we're seeing this increase in mortality. So some of the other work that I was presenting were actually building things like forest density into their models and still finding a signature for climate. So there's ways to account for it, and that's one of the first go-to things that we thought of too.
Okay. Dennis Murphy sort of has a related, more sort of management take on the same question, but he asks, is there a combined stress effect of drought and high-density stands that could be mitigated through thinning and or prescribed fire?
Yeah, I think the two things are definitely going to interact with each other. Unfortunately, with the Park Service and Forest Service data that I was showing you, we didn't really have a good estimate of density in those stands. We weren't sure if we were really capturing all the trees in our observation plots. And that's one thing I'd like to look into as far as that relationship goes. That being said, yeah, I would expect there to be patches of where if you sort of have more straws in your milkshake, if you have more trees on the landscape, and you start drying it out, I would expect those areas to be more sensitive to fire and probably also any sort of changes in what the water deficit looked like.
Okay. More straws in your milkshake. I like that. I like that analogy there. That's good. Okay. Jeff Manley asks, could burning with a cooler prescription reduce mortality under this model?
We'd expect that. And first of all, I'll say hi, Jeff. Just again, if you're sort of reducing the amount of or reducing the severity of the fire injuries to trees, you'd expect a less mortality. Whether you want to do that as a manager or not, that's sort of up to your goals. We had some discussion back and forth whether if the goal was to reduce, say, ladder fuels, maybe burning under a drier context would be a good thing. You'd take more of them out.
Right. Okay. And question from Alex Victoria. when we talk about the future conditions of ecosystems, we frequently talk about desired future conditions. Recently, however, I've heard the discussion framed in terms of undesirable future conditions.
That's kind of a good point. And that's what we're seeing, especially in the southwestern forest, is that climatic conditions are going towards an area where if you want to conserve these areas or preserve them, if that's your goal, it's going to be increasingly difficult. A lot of these forests, if you look in sort of the Four Corners region, they're already on sort of their physiological limits of what's of a landscape that's going to be able to support a forest. And so if you, the big trees there are fairly resilient to a lot of stressors that are on them. But if you start adding things like fire that's going to kill them directly, what's going to come back? And that's sort of a big unknown and kind of a big worry for a lot of people. Likely things like invasive grasses, shrubs might come back rather than forest. So again, if your goal is conservation, this could be a big problem.
Okay. So Devin Barnes has a big question here, sort of the $10 million question. Since financial resources are limited for land managers, which programs would you allocate funding to? Would you mitigate the symptoms such as pest and disease infestations, fire severity, etc., or treat the underlying causes of being climate change? So what, I guess what maybe a way to rephrase that is sort of which of the stresses, I imagine I'm sure it's location dependent, but which of the stresses is probably the broader, more general threat that we could actually maybe start tackling?
Yeah, that is a tough question, and I agree with you that it's going to be very context dependent. Probably, these landscapes are going to respond one way or another, whether we sort of apply management to them or not. But they're probably going to adjust in ways that we don't like. So given resource dollars, there's been talk sort of kicked around, well, if we can't do everything, maybe we could start having a triage sort of program. And nobody really likes that idea, but I think that's probably realistic, where we have some areas where we think, okay, management is going to have some benefit to us. It's probably a no-regrets sort of thing if we try to restore a fire regime in some areas that historically burned a lot, and it might make it more resilient to future fires, or if you thin it out, it might be more resilient to future droughts. But we probably won't be able to achieve that everywhere. And so you'd have to sort of pick your marquee areas that you'd want to really focus on, and the rest will adjust one way or another. And it's not a great answer, but that's probably the realistic answer.
Right. Okay. Alex Victoria has another question. He wants to know if the NPS, the National Park Service scenario planning, uses this perspective.
Again, it's sort of context dependent. And I would refer people to Lee Welling, who is the person who's sort of heading that up with the Park Service. And each park is going to have their different challenges. So a park in the desert Southwest is going to be different than, say, North Cascades or something on the East Coast. But so they're trying to develop the scenarios that are specific to a park. And obviously, I think that's the smart way to go. And I'm not sure if that's getting at what she's asking, or if she's trying to, certainly with some of these areas that are already sort of arid, they're looking at things like, what if drought becomes more frequent? What if fire becomes more frequent or severe? So I guess yes is the answer to that.
Okay. John Dawson wants to know if do we know enough about the rates of a changing climate to incorporate into forest management and near-term decision making?
Do we know enough about the rates of changing?
Yeah.
Again, it will be context dependent, which is not a great answer. Some of these areas, like the Southwest, I mean, we're seeing changes already. So I would say probably to that. A lot of the stuff that I was showing you in this talk was things that have already occurred. So it's climate change isn't something that's happening in the future. It's happening now. It's unfortunately it's something that we expect to get worse going forward. So exactly trying to understand all the sort of ins and outs of it is probably going to be beyond us. But if we can get to some management decisions that we think will be no regrets, things that we'd want to do anyway, but maybe we tweak them a little bit. Say if we're planning on a prescribed fire, maybe we'd want to increase the interval that we're doing our prescribed fires. or increase the severity of the prescribed fires. So put your burn lines a little further apart so we can have higher fire intensity or something like that. So again, you know, if it's at the stage for sort of near-term decision making, that's a tough question. But you know, it seems like we need to start at least doing some experiments.
Right. The next question I think kind of falls under your no regrets strategy, but Brad Peel wants to know, one of our approaches is to try to increase species diversity where possible, including created openings. Do you think that is a reasonable approach to dealing with climate uncertainty?
I think that would be one good way, because we don't really know who the winners and losers are going to be in terms of species that are going to respond to it. So, you know, like the questioner sort of implies here, that there's going to be a variability in response. Some species are going to respond better to this sort of conditions than others. So there's also some physiological evidence to back that up, and probably some genotypes as well. So yeah, I'd say increasing species diversity is probably one tool that you could put in your portfolio to try to make sure that you have a forest stand going forward.
Okay. Margaret Click asks, do you think that trees that have experienced drought are more susceptible to additional drought because there's been some sort of internal damage that causes the tree to be less efficient or able to absorb water? Or is there some explanation of why this happens? Is there anything we can do to help the situation?
I'm not sure if there's anything we can do to help the situation, but that's what the sort of recent, if we're looking at drought, the sort of mechanisms that are killing trees is still sort of up in the air. And so there's some things that I was talking about today, like this cavitation fatigue, where trees essentially that are drought stressed, looks like the xylem in them is having a harder time sort of rebounding back from a cavitation. There's also some ideas that trees that are drought stressed will close up their stomata where they're transpiring water and sort of doing gas exchange. And as a result, they're conserving water, which is great, but then they're also running out of carbon, so they're not absorbing carbon at the same time, so that they might in fact starve to death. That might be one mechanism. And likely a lot of these things are probably going on, and they're probably more important in some species than others, but it's still an area of active research.
Okay. Tony Kerwin asks, in this work, did you document any vegetation species shifts in the recovering forests likely due to climate change, or is it still too early to see that?
It's still too early. That's one of the things we wanted to explore with some of the data that we have. We just haven't gotten to it yet. I doubt if we'll see big changes, at least with the data sets that we're looking at, but that's sort of up for grabs. One of the things that I should mention with some of the work I was showing you was mostly, well, in fact, it's almost exclusively prescribed fire. And that's well and good for a subset of the things that we're looking at. But when we have big patches of severe fire, that might start changing. So, you know, looking at the forest reproduction and how that changes in the future, I think is a big question. And I haven't seen a whole lot of great research on that yet, but something that needs to get done.
Right. Jennifer Evans wants to know if there's been any similar studies done in the eastern U.S. and if not, do you anticipate that there would be similar results if it was done there?
There is some stuff looking at mortality and its sort of sensitivity to drought in these areas in eastern forests. So, you know, that it'll have the same sort of effect in eastern forests that we'd expect here in broadleaf forests. What the projections are for those areas, I'm not exactly sure. I remember hearing something about it, and probably no one should quote me on this, that one of the problems in, at least in the Northeast, is that they currently don't really experience fire in those forests very often, and they don't really have the infrastructure to deal with it. But as things essentially warm up and dry out there, that they're expecting an increase in fire activity in those forests, and how these stands will respond to that and how management might respond to that is sort of up for grabs.
Right. Okay. Sharon Hood asks, do you think waiting to prescribe burn for a few years after thinning would help or allow trees to recover from drought stress so that there is less fire-caused mortality?
I'd expect that to be true. I don't know if there's been research done to present that, and Sharon might actually know. Again, if we going back to the straws and the milkshake analogy, we would expect after thinning, once the trees have more or less recovered from the management activity, that we'd expect an increase in growth rate. So we'd expect essentially a higher vigor of those remaining trees, and they'd probably be likely able to survive fire better. But I can't think of anything that's actually demonstrated that, but that would make sense.
Right. Okay. Well, Phil, that was the last question. I want to thank you for a great presentation. This is, a lot of our audience out there is struggling with these questions, and these rapid changes that are occurring. Everyone's trying to adjust their strategies and their perspectives, and this is a valuable contribution to that in terms of trying to figure out what's happening out there and how we need to change the way we go about business in response. And I look forward to seeing more of this work.
All right. Well, thanks for the invitation, and thanks again for everyone for taking time out and dialing in and all the questions.
Okay. Thanks, Phil. And just as a reminder to everyone, we are recording the webinar, and I'll upload the webinar here in a few minutes as soon as it's finished spinning all its wheels. And we'll have it available on the Advances in Fire practice page. You can Google that, and you can get there. It's right up. It should be right up at the top. And we look forward to seeing you guys in the next webinar. And thanks for coming. And thanks, Phil.